Hi, in this video I will be very thoroughly solving the puzzle Bubbly from the 2019 MIT Mystery Hunt by Sammy Casanova and Jesse Gellis. This is not a standard solve-along video in that I'm not working out the solution for the first time. I already know the solution and I will be spoiling it fairly early in the video. This video is more educational and you're meant to be able to follow along. There will be a lot of working out examples and diagrams on the screen. I will be coding a solution in Python and also working out a technique to solve the puzzle by hand without programming and working out the entire solution that way as well. Along the way, I will be introducing some important concepts in combinatorial game theory and using them in the solution of the puzzle. This video is probably not for everyone, so don't feel bad if you decide to give it a shot and decide not to watch the whole thing. But I do recommend the puzzle for anyone interested in the topic of combinatorial game theory. It's a much-loved field of recreational mathematics and a main research area of John Conway, among others. Okay, required background for this video. I will be introducing the basic concepts of combinatorial game theory, so I don't assume that you have any knowledge of that field. I will be using topics from discrete mathematics that you would typically get as a first-year mathematics undergraduate or earlier. Set theory, graph theory, mathematical induction. So some experience with those topics wouldn't hurt. At the same time, the concepts I'll use are pretty intuitive and I'll be taking a very practical approach. The goal is not to prove any formulas, but just to understand them well enough that we can apply them to solve the puzzle. I'll be pretty casual with the notation too. I'd say if you're interested, you can give the video a shot even if you don't have much formal background with discrete mathematics. As for the coding parts, if you don't know Python, then you won't completely understand them, but I think that's okay. The code is mostly part of the video to be an illustration of the concepts. Sometimes just seeing something written a different way can really go a long way with understanding. And if you don't follow the coding parts, by the end of the video we will have a complete solution that doesn't require any coding at all. Alright, if you're still interested, let's go. Alright, let's start by reading the puzzle. New Year's Town, Bubbly. Ray and Blanche sit down with their jug of champagne to play a game of Bubbly. Blanche, as she always does, goes first. Blanche surveys the opening state with a smile and pops bubble S. Okay, so this is the opening state on the left here, and when she pops bubble S, that means that S is no longer part of the state. You see after that, the S bubble is gone. Now it's Ray's turn, and he chooses to pop bubble H. Since it's impossible to pop H without popping both A and E, which surround H, A and E are popped as a consequence. So by choosing to pop H, that means that after Ray's turn, all three of bubbles H, A, and E are gone. It is Blanche's turn again, and her move is to pop bubble T. And you notice that when she pops T, I is still there after her turn. You've got me, I resign, says Ray. If I pop I, you win with N as the last possible move. And if I pop N, you win with I. So this is basically explaining that whoever gets to their turn and is unable to go, they're the loser. And that's what the flavor text is hinting at. In New Year's Town, you never want to run out of champagne. So in this case, Blanche wins. Don't worry, says Blanche, you never had a chance. I was guaranteed to win as long as I started with bubbles E, N, or S. So this is saying that if Blanche had started by choosing E, or N, or S, which she did, then she would have been able to guarantee that she could win. All right. So this section here is explaining the rules of the game. And then it says, what are your winning starting moves? And it has 7 different, much larger games. All right, and that's it. So obviously the idea is to analyze each of these games. And like Blanche said here, figure out what are the letters in the starting moves for each of the 7 games, and then combine them in the right way. Okay? Okay, let's take a look at the written solution to this puzzle. So there's some information in here, but the main thing is just that it shows the winning moves for each of the games. So in the first one, it's showing that I and E are the winning first moves of the first game, and same with the others. And then it shows how to combine them. It's pretty straightforward, but I'll come back to that. But what is not shown is any write-up of how you actually determine that it's I and E. There is a program in Python that's here, and you see at the end it shows the output of the program, and in each case it shows one of the games and the winning moves for that game, E and I in the first case. So you could read the source code of the program in order to figure out how you're supposed to find the solution. But the reason they don't go into much detail is because this is a fairly well-known class of games called impartial games. And in particular, it's a variant of Nim, which is a very well-known game. So that suggests an approach that will let us solve this. So our goal is essentially to write a program like they have that solves it using the technique of impartial games. And we're also going to develop a method to solve it by hand. And so once we have that, we've pretty much solved the whole puzzle. Okay, let's step back and consider a very simple board game. So for this board game, I'm going to draw some squares here. That looks pretty good. Okay, I'll put a S in the starting square here. And I will just draw some arrows connecting the squares. Alright, I think that looks pretty good. So the rules of this game is there is a game piece, and you take turns moving the game piece. So the game piece starts here on the starting square, and the first player can move it from this square to any square that it has an arrow pointing from. So it could move to this square. And the second player moves it from this square to any square that it has an arrow pointing from. So it could be here. And this goes on. The first player moves again, the second player moves it again, so on, until eventually it gets to a spot where there's no arrows coming from it. At this point, whoever's turn it is loses because they can't make a move. Alright, so definitely a very simple game. And think about if you were playing this game and you had time to prepare, what would your strategy be? And if you think about it, this game has a lot of similarities to Bubbly. 2 players take their turn. There's no score. The players don't have pieces of their own. They're sharing a piece when they move it around. And if it's the first player's turn in this state, then they have the exact same options as if it's the second player's turn in this state. So these properties are what makes this what's called an impartial game. And Bubbly is another example of an impartial game. One thing that's important about this game that might not be obvious is that there's no loops. There's no way to get back to where you started. There's no way to ever revisit a square. And that's important because that means the game has to end. It won't go on forever. So given all those properties of an impartial game, it's guaranteed that either the first player will definitely be able to win, or the second player will definitely be able to win. There's no randomness involved. One player definitely has a winning strategy. Okay, so for this, I'm going to define a couple of symbols. Blue circle and a red X. Now the blue circle is what I'm going to call a good state. This is also known as a first player win. And the red X is going to denote a bad state. This is a first player loss or a second player win. So what we need to do is go through each of these squares and determine whether it's a good state or a bad state. So of course you start with the ones where you can't make a move. So if the token is here on your turn, you've lost. The other player has won. So this is a bad state. Same with this one, there's nowhere to move from this square. Okay, now, any square that you can get to a bad state from is going to be a good state. And if you think about that, that makes sense. So if the token is here on your turn, you can just move it to this one, and then your opponent will lose. And that's true of anywhere that you can reach a bad state from. All right, what about this square here? If the token is here on your turn, then you have two options. One is you can move the token here, but since this is a good state, that means you're putting your opponent in a good state, and your opponent will win. Or you can move it here, but this is also a good state. So if you move here, then your opponent will also win. So you don't have a choice that will let you win in this case. Neither of the two options will let you win. So this is a bad state. All right, what about this? So in this one, you have a choice. If the token is here on your turn, you can either move it to a bad state or move it to a good state. So of course, you're going to choose to move it to a bad state. If you move it to a good state, then your opponent will win by moving it to a bad state. So when you have the choice, you're still in a good state because you have the option of moving to a bad state. So same here, you have the option of moving to a good state or a bad state. Of course, you choose a bad state. So that's also a good state. And so anything that points to at least one bad state is going to be good. All right. Now, what about this one? If the token is here, you have four options. You go to this one, which is a good state. This one is a good state. This one's a good state. This one's a good state. So no matter where you go, your opponent is going to be in a winning position. So from here, you have no chance of winning. So this is a bad state. Okay. And finally, we get to the starting position. So starting position, you have four options: good, bad, good, good. So you have the option of going to bad, so this is a good state. So the general rules for this analysis are, as long as you have the option of moving to at least one bad state, then you're in a good state. And if all of your options are good states, then this is a bad state. And this is true even if you have no options. You have to have at least one option that is a bad state in order to be a good state. So analyzing it this way, we can see that from this starting position, this is a first player win. You will win from this position if you follow the strategy right. And the only way to win, the only move to make from here that is a win, is to move here to this bad state. And generally, you always want to move your opponent into a bad state. So for instance, if the opponent goes here, then you want to go to the bad state option, which is here. And then your opponent might go here, and then you can go here and win. Okay? So you can see that this strategy will always let you find out from any given position what are the winning moves. It might be much bigger and more complicated, and it might take more time, but this analysis will work to give you a strategy for any arrangement of states. Okay, so we know how to solve this board game, but how does that help us solve the game of Bubbly, which is what we want? And the simple answer is that every game of Bubbly can be transformed into a board game with a different graph by taking each of these states that the game is in after each turn and turning those into squares on the graph. All right, so this is the images copied from the puzzle into a graph, and these are the moves that the players made. And there's a lot more that are not represented on here. So we can do the exact same thing by determining whether each of these states is a good state or a bad state. So see in the puzzle here where it says, "You've got me, I resign. If I pop I, you win with N as the last possible move, and if I pop N, you win with I." So what Ray is saying here is that the state that the game was in at that point, which is this one, is a bad state. And he's saying because if he pops I, then Blanche will pop N and get to this state, which is the end state with no bubbles left to pop. So there's no moves from here. And if he pops N, then she will pop I and also get there. Okay, so Ray was able to see the rest of the graph from this point. And Blanche says, "You never had a chance. I was guaranteed to win as long as I started with bubbles E, N, or S." So what Blanche is saying is that the starting state was a good state, and that this state here, after her first move, was one of three possible bad states as you could reach from the initial good state. So there's 2 more out here as well. And so you can see what happened every turn is Blanche would move to a bad state, and then Ray would be forced to move to a good state. And then Blanche would move to a bad state, and then Ray again would be forced to move to a good state. So in order to determine which of these were good states and which were bad states and everything, you need to be able to analyze more of the graph, which Blanche was able to do from the very beginning. So let's go ahead and analyze the graph for this example and see if we can confirm that the 3 winning moves from the starting position are popping bubbles S, E, and N. Okay, so what do you need in order to build the graph and do this analysis? So you need a way to represent the states that the game can be in. We have a picture here, so that's taken care of. And you need a way to determine from any state, what are your options? What other states can you reach directly from that state? So let's do that for this example here, just to get started. So I'm going to rewrite this state. I'm going to leave out the letters for one thing. We can always figure out, looking at this, where the letters were to begin with. You put them on a line like this, just so it's a little more systematic. Okay. So there are 7 bubbles in this state, and on your turn, you can pop any one of the 7 bubbles. So there are 7 options to get to from here. And it's good to go about this in a kind of systematic way. So let's first look at the options that remove 1 bubble, remove 2, and remove 3. And so we'll go down each of the 4 outer bubbles and remove 1, and then remove 2, then remove 3. Okay, so first up, popping this first bubble, we'll remove 1. And so this one will be completely gone. I'll just mark that with a dot just to remember it was there, but it's not part of the game anymore. And then the others are untouched. So this one's still there, this one, and this one. All right, now what if you pop the second bubble? That also removes 1. All right, for the third one, if you want to remove 1, you just pop the outer bubble and leave the inner bubble there. So this bubble within a bubble just becomes a single one. And then if you pop the outer bubble on the last one, you'll get this. All right. Now, what if you remove 2 bubbles at a time? You can't do it with either of the first ones. If you pop one, there's no way to also pop a second one. In this case, if you pop both the inner and the outer bubble, you remove both. So that will get you to this state. And for this one, if you pop the 2 outer bubbles, then you'll just be left with a small inner bubble. Okay, and what about removing 3? The only way to do that is to pop all 3 on the outer bubble. Then you're left with this. Okay, 7 possible options here. Now I'm just going to mention that this is exactly equal to the setup in what's called the game of Nim that was mentioned in the puzzle. Nim is the most famous impartial game. So with Nim, it's a very similar idea. You have stacks of stones, and on your turn you can remove as many stones from a single stack as you want. So popping the outer 2 bubbles of the last one here corresponds to taking the top 2 stones of this stack here. Later on we'll see how some bubbly states are different from Nim states, but this bubbly state corresponds exactly to this Nim state. And so doing this bubbly analysis is the same as doing a Nim analysis. All right, so that's the basic idea. Now before we actually build the graph, these circles are not very easy to draw. It's easier to see and write if we represent these a different way. So I'm just going to, when I have concentric bubbles like this, I'm just going to refer to it by the number of concentric bubbles. So this state here, I'm going to call 1, 1, 2, 3. All right, so that's saying bubble, a single bubble, a single bubble, a bubble within a bubble, and 3 concentric bubbles. So for each of these, you can also assign them a number like this. Okay, a couple more minor things. So once it gets to 0, it's out of the game. So we can just completely ignore it. So we can just write this as 1, 2, 3, and this as 1, 1, 3, and this is 1, 1, 2. Also, these two states are exactly the same. I know we popped a different bubble, but as far as who wins is concerned, whether it's a good state or a bad state, they're exactly the same. The order of the bubbles doesn't matter. You can rearrange them however you want. It is true that if we want to see which letters we need to pop in order to win, we are going to have to come back to look at this. But for the purpose of just analyzing the graph, these two states are exactly identical. So I'm just going to write these both as a single state called 1, 2, 3. It doesn't change anything if there's more than one way to go from one state to another. And this state here, I'm going to call this 1, 1, 1, 2. Because it's a little more systematic to keep these numbers in order. Just keep in mind that we can completely change the order of the numbers. It doesn't change whether something is a good state or a bad state. And then when we have to go from 1, 1, 2, 3 to 1, 1, 1, 2, we'll have to think for a minute, okay, how does that happen? In this case, you pop 2 of the 3 to get this 1. This will make it easier to analyze the graph. So I'm going to write this as ops, as in the options you have from this state. 1, 2, 3. 1, 1, 1, 3. 1, 1, 2, 2. 1, 1, 3. Again, leaving out the 0. 1, 1, 1, 2. And 1, 1, 2. All right, so in the actual graph, this is how I will represent states. And so from this state, I'll have 6 arrows pointing to each of these 6 states. All right, let's add that to the definitions here. Okay, so now let's make the real graph for this starting state. I'm going to start by dividing up the graph. And each of these divisions is going to be the number of bubbles that are left in the state. So we'll start with 7 at the starting state over here. 6, 5, 4, 3, 2, 1, 0. We'll just put the state in whichever category has the number of total bubbles that are left. It'll just make it a little easier to follow. Start here with the starting state. 1, 2, 3. All right, and now all of the states that you can reach from this one. First of all, when you remove 1, you're going to wind up in the 6th column here. All right, if you remove 2 from this, you'll wind up in the 5 column. Then you get 1, 1, 2, 1, which we said we're going to write as 1, 1, 1, 2. If you remove 3 bubbles from the last one, you're going to get 1, 1, 2 here in the 4 column. Okay, you don't have to put the arrowheads on here because we know the game always proceeds from left to right because you're always removing bubbles. Okay, great. So now we have to do that for every other state. So let's start with this one, 1, 2, 3. If you remove 1 bubble from 1, 2, 3, you can either get 2, 3, or 1, 1, 3, or 1, 2, 2. All right, if you remove 2 bubbles from this, you can either get 1, 3, or 1, 2, 1, which is the same as this one, 1, 1, 2. And finally, if you remove 3 bubbles from here, the only way to do that is to get 1, 2. Okay. Now, this one, if you remove 1 bubble, there's 3 ways you can do that to get to 1, 1, 3. Or you could remove 1 from the 3 and get 1, 1, 1, 2. If you remove 2 bubbles, you'll get 1, 1, 1, 1. And finally, you can remove 3 bubbles and get 1, 1, 1. All right, 1, 1, 2, 2 can become 1, 2, 2, 1, 1, 1, 2, 1, 1, 2, and that's it. There's no way to remove 3 bubbles from this at a time. All right, 2, 3, you can remove 1 bubble to get 1, 3, or 2, 2. You can remove 2 bubbles to get just 3. Or 2, 1, which is the same as 1, 2. Or remove 3 bubbles to get just 2. Okay, and we'll just keep doing all the rest of these. All right, when you have just one set of 3 bubbles, you can pop 1 to get 2, pop 2 to get 1, and finally if you pop all 3, you get to, we'll call it the 0 state. It's just where there's no bubbles left. We could also just leave it empty. Okay, so this is not too bad, but it can get a bit confusing. Like, see, this one has 6 states pointing to it on the left, and it's pointing to 3 other states on the right. So we're going to have to be a little bit careful working with this graph. But if you're careful, you should be able to work with it. Great. So now we're going to take this graph and we're going to fill it in with good and bad states like we did before, remembering our rules. If something points to only good states, then it's bad. If something points to at least one bad state, then it's good. And we're going to start here on the right. This state does not point to any states at all, so obviously it doesn't point to a bad state, so this state is bad. And now everything that points to this state is going to be good, because anything that points to at least one bad state is good. So it's this one, and this one. These are the 3 that point to this state. All right, so now we step up, and we see this question's already answered, so we can step up again. This question's already answered, and we get to this one. This one is pointing to only one state, and it's a good state, so this is a bad state. And again, anything that points to this state is going to be a good state. So there's 5 other states pointing to it. So it's this one, this one, this one, this one, and this one. All right, and now as we step up, we'll see that a lot of them are already filled in, which is nice. And in fact, anyone that's not already filled in is going to be a bad state. So like this one points to 2 others, and we see that they're both good states. So this one's bad. Same here, this one only points to 1 other, and it's good state, so this one's bad. So anything that points to either of these states is going to be good. So in this case, 2 states are pointing to this one, and 2 states are pointing to this one. Keep stepping up. The next ones that are not filled are this one, which is pointing to 6 different states, and they're all good states. So this one is bad. This one's pointing to 3 different states, and they're all good states, so this one is also bad. And of course, anything that points to either of those is going to be good. Okay, so we filled in the whole graph. It wasn't too bad. So this answers the question, is the starting state a first player win or not? And it is. Now, you might be wondering, did we have to fill in the entire graph in order to answer that question just for this one state? And the answer is not necessarily. You can do it either way. We started on the right and went to the left, but you could also start on the left and go to the right. And the way you do that is by leaving questions unanswered temporarily. So imagine asking the question, is this state good or bad? In order to answer that, we need to ask each of the ones that it can reach, is that state good or bad? In order to answer that, we need to ask each of the ones that can reach, is that state good or bad? And so we keep these questions partially answered until we come back to them. And eventually we'll get down and ask this one, is this one good or bad? This one's bad, we can't answer that. So that propagates back up. That lets us fill in the answers to the ones we had pending and gets all the way back to the top. And in this case, that would save us a little time because this first one happens to be a bad state. So as soon as we've answered this, then we can immediately answer that the first state is a good state. And we won't have to answer the question for any of the ones on the bottom here that aren't reached by it. But in general, that's not going to save you a ton of time. It's going to be about the same starting from the left and going to the right, or starting from the right and going to the left. Right to left is called dynamic programming, and left to right is called recursive. And when we write a program to solve this, we're going to do the recursive way, where we start from the left and go to the right, just because it's a little simpler conceptually. But it's not to save time, really. It's just because that's going to be an easier way to express in terms of programming. So, in fact, we didn't just want to answer the question of whether the starting state was good or bad. We also wanted to answer the question of which of the starting moves is a winning move. So that's everything that you can reach from the starting state that is a bad state. And in this case, it's 1, 2, 3 and 1, 1, 2, 2. Okay, so let's go back to the puzzle and see what this answer means in terms of which bubbles to pop. So this is the starting state, 1, 1, 2, 3. And we said that the winning first moves are 1, 2, 3 and 1, 1, 2, 2. So what does it mean to move from 1, 1, 2, 3 to 1, 2, 3? In that case, that means popping either of the ones that are just a single bubble. Like Blanche did here. Blanche moved to 1, 2, 3, and that leaves Ray with these 3 bubbles. Okay, so S would be a winning first move, and N would be a winning first move. You could also go from 1, 1, 2, 3 to 1, 1, 2, 2. And what would that mean? That would mean popping the outer bubble of the 3 and leaving just the inner 2 bubbles there. That would also be a winning move. So that means popping bubble E. And so you'll see here, that agrees with what Blanche says. I was guaranteed to win as long as I started with bubbles E, N, or S. Okay, so our answer matched with what the example puzzle says. So that's great. Okay, so is that it? Are we ready to solve the full puzzle by hand? The answer is no, and it's just a matter of scale. So this graph has 19 states in it. A graph for the full puzzle is going to be much larger, and it's just going to be too big to do by hand. But what we can do is write a program to do it. So let's do that. I'm going to call this nim.py. Just because this first program is only going to be able to solve the Bubbly configurations that are equivalent to nim games that I mentioned earlier. We'll do a full Bubbly solution after this. This is going to be a pretty short Python program. I'm not going to explain every line that I write, but I will go into a little detail of the lines that encode the concepts we're using. All right, the first thing we're going to need is a function that, given a state, will tell you all of the options for that state, all of the states that you can reach directly from it. This is not going to be super clear, but I'm looping over every number in the state and every possible smaller number than that number, and I'm going to define a new state that replaces the number with the smaller number. Okay, so that's what this function does. Let's test it out. we'll use our favorite starting state here. Okay, so we're just going to loop over all of the different options for this starting state and print them out. All right, there they are. So the first one replaces 1 with 0, the first one with a 0. Second one replaces the second one with a 0. The next two are replacing the 2 with a 0 and a 1. And the last three are replacing the 3 with a 0, 1, and 2. So these are the same 7 states we saw when we were doing it by hand. As before, we're going to get rid of these zeros and put them in order. Just so it's a little easier to read that way. And I'm not going to explain it, but that's what this line does. This just puts them in order and removes any zeros. Let's try running the program again. Okay, yep. So this is more like how we were representing the states by hand. And you see there's still 2 1, 2, 3s here. We could get rid of the duplicates, but it's fine. It should be fine just to leave them as well. All right, so next we can define the isGood function. And this will return true if the state is a first player win, a good state, and false if it's a second player win, a bad state. Okay, and it's just one line, and this line is encoding our rule, this rule, that something is a good state as long as not all of the states you can reach from it are good states. Not all is good S1 for S1 in ops S. So it checks whether all of the states that you can reach are good states, and if they are, then it returns false, otherwise it returns true. So let's test this out. So we're just going to print out whether this is a good state or not. It should be true, as long as I haven't made a mistake. Okay, great. So we want to know that. We also want to know what are all the possible winning moves from this state. So the winning moves from a given state is going to be any move that you can reach from it that is not itself a good state. All right, so let's test out this function. Oops. Okay, so it's saying that the winning moves from the starting state are 1, 2, 3 and 1, 1, 2, 2, which agrees with what we said here. 1, 2, 3 and 1, 1, 2, 2. All right, cool. So this seems like the program is working. And as you can imagine, we can do this for larger states as well. So from this starting state, 2, 3, 4, 5, what are the winning moves? Let's try this out. You see the program is definitely taking longer now. Oh, so this one must be a losing state. Yeah, actually, all right, so this is a bad state. So there's no winning moves if you run with this one. Let's try one that is not a bad state. Yeah, okay, so this one's not a bad state. Okay. All right, so that's a winning move. That's a winning move. That's a winning move. You can see the program is definitely taking much longer to run now because the graph is much bigger. So these are the 3 bad states you can reach from 3, 4, 5, 6. The reason the program is so slow is that it's duplicating a lot of work. So when it's going through this graph, it is visiting these states multiple times from different places, and every time it's recomputing whether that state is good or bad. So all we need to do to speed this up is to tell it, when it calls this function, to remember what the answer was last time it got called, so that it doesn't redo a bunch of work. just tell it to cache this function. So now whenever it calls this function with a state that's already called before, it'll just remember what it returned last time and do the same thing. So now this should run much faster. Yeah, pretty much instantaneous now. And one good thing about keeping the cache is that it remembers how many times this function's been called. So this is going to tell us how big the graph is, how many different states are getting sent to this isGood function. So I'm going to print that out when it's done. Current size of the cache. Okay, so it's going to print out the winning moves, and then it's going to print out the size of the cache for the isGood function. Yeah, 152. And you can imagine if we did a much larger starting state. It still goes very fast, but the graph is getting much larger, 6,800. So this is probably more in line with the size of the graph for the puzzles we'll have to solve. So that's why we can't do this by hand. All right, so this exact same approach is what we're going to use to solve the puzzle using a program. To solve the puzzle, and in general, just to solve any impartial game, what you need is two things. You need a way to represent states, and you need a way to determine, given a state, what are all of the moves that you can make from that state. So we're just going to take the same program, but just replace the ops function and the starting state with what's appropriate for the game of Bubbly. Again, this is the starting state here. We need to represent this somehow in the program and be able to say, given a state like this, what are all the states you can reach from it? So let's start thinking about that. So we've already seen for states that are just a bunch of concentric circles, we know what all the options are that you can get to from here. You can pop 1, 2, 3, or 4 of these bubbles. This dot is just representing the empty state where there's no bubbles left. So we want to be able to say the same thing, but for states that are not just sets of concentric circles like this. All right, what about a state like this? All right, so let's just look at this example and see what the states are. So there's 4 bubbles here, so there's 4 possibilities. We know you could pop the outer bubble, and then you're left with 2 inner bubbles here and 1 here. All right, you could pop the outer bubble and the middle bubble here, then you're left with 2 like that. You could pop the inner bubble on the left, and you're just left with the inner bubble on the right. Or you could pop the inner bubble on the right, and you're just left with the 2 on the left. All right, now notice that all of these, we have ways of representing this using the numbers from before. This would be 2, 1, 1, 1, 1, and 2, using the notation we were using earlier. And this, I don't know, I mean, we're not going to wind up using this, but we might say this is 2, 1 inside a larger circle. So in this case, there's one state, which is just what you get if you remove the outer circle. And then there's 3 more states. And notice that these 3 states are all ones that you could get to from this state. Right? So in general, that's always going to be the case. So you're going to have one state, which is just popping the outer bubble. And then all of the states that whatever's inside that bubble can reach, you can also reach in one move. So the way I'm going to write that is, for any state inside a single bubble, this is going to be the state itself that's inside the bubble, and any state that you can reach directly from that state. All right, so this is one rule that's going to help us. As an example of this rule, suppose we didn't have this n here, we just had the big bubble C. The state that's inside that is 3 bubbles, G, R, and H. So from C you could reach the state that's G, R, and H, or you could reach any state that you can reach in one step if you started with G, R, and H. Okay? Now, what if we don't just have a simple state inside a larger bubble? Let's take a look at a more complicated example. And I'm going to start adding in the letters just to make it easier to follow. All right, so this state is going to consist of two bubbles, and each of them is going to have more bubbles inside them. So we'll call this one A, and it contains two bubbles like here, which we'll call B and C. This one will be called D, and it contains a bubble E that itself contains a bubble F. Okay, so we know that there's going to be 6 states that you can reach from this state, and we can write them all out. But let's define S1 and S2 as the two parts that make up this state. So by that I mean S1 is just the A bubble and everything inside it, and S2 is the D bubble and everything inside it. Cool. So now each of these two sub-states are ones we already know how to list all the options for. So this one uses the rule we just saw. The first option is going to be if you just pop the outer bubble. And in addition to this state, it's everything you can get to from this state. So if you pop B, you'll get C. And if you pop C, you'll get B. Okay, so these are the options for just state S1. And S2 is also something we've seen before. This is just 3 concentric bubbles, so we can pop 1, 2, or 3 of these. If we just pop the outer one, we will get E and F. Right? If we pop E, we'll just be left with F. And if we pop F, we have nothing left. So that's just the empty state is also an option for S2. Okay, so I'm going to write down the rule for S when it's made up of 2 states like this. Then I'll show you what I mean. So the rule is going to be ops of S1 plus S2 and S1 plus ops of S2. Okay, so let's see what that means in this case. So ops of S1 we know is these 3. So I'm going to copy these down. Okay, and we want to add each of these 3 to S2. All right, and S2 is this one. Okay, so these are our first 3 options. In addition to those 3, we have 3 more options that are S1 plus the options of S2. So I'll start by copying S1 down 3 times. And I'll add to each of those the options from S2, these here. And in this case, this is just the empty states. There's nothing to copy. This is just going to be, you're just going to be left with S1. Okay, so there you have it. These 6 states are the options for S. And if you want to verify, you can see that if you took this starting state here and you pop bubble A, this is what you get. If you pop bubble B, this is what you get. Okay? So here is the general rule that we'll use in this case. Now, if we wanted, we could say, what if you have 3 states, ops of S1 plus S2 plus S3? But that's not necessary. If you had like 3 bubbles that had more bubbles inside them, what you could do is you just pick one of them to be S1 and the other 2 together to be S2. And that's fine. It still works out. And you just apply this rule once here. And then when you want to get the ops of S2, you have to split that into 2 smaller states as well. So this is really all you need if you want to handle multiple bubbles. Okay, so between this rule for multiple bubbles And this rule, when you have just a single bubble, we can build up the options for any state we want. The only case we don't have covered with these two rules is the empty state, because we don't have multiple bubbles and we don't have a single bubble. But in that case, it's pretty clear. The empty state just has no options at all. All right, let me copy this over so they're together. Oh, also, just because I want S to refer to the overall state, I'm going to call this S sub 1. So in this case, the state S is a bubble containing S sub 1. All right, now let's try to implement these two rules in Python. First, I'm going to rename this to bubbly.py. Okay, so we need to redefine the ops function, and we need to represent the state in the correct way. All right, so as a starting example, let's take this state here. S equals these two bubbles. So S sub 1 is a bubble containing two bubbles that don't contain anything. So the way I'll do a bubble that doesn't contain anything is just an empty tuple. So that's two bubbles that don't contain anything. So this is the state inside of A, and this is the state that contains A. This is S sub 1, A and the contents of A. It's very tricky in Python to forget this trailing comma. So just as a general rule here, I'm just going to be adding a comma after every close parentheses, whether it needs it or not. So DEF is going to consist of a bubble containing a bubble containing an empty bubble. Okay. Again, I'll put a comma after every close parentheses. So this representation of states, it can be hard to read, certainly, but it's probably the most intuitive. If you imagine lining up all of the bubbles in the state along an axis down the middle, then you can sort of slice into it. And then the state representation in Python, every time you enter a bubble along this slice, it's an open parenthesis, and every time you exit a bubble, it's a closed parenthesis. And then we just make sure to add a comma every time we exit a bubble as well. So that's why I like this representation, but again, it's not the only option. So now let's handle the opts function, and there's two cases we need. One is when S just consists of a single bubble. Okay, then we want to call S sub 1 the bubble that's contained inside it, or the state that's contained inside it. S sub 1 may consist of more than one bubble, but it's just any state. Okay, and then we want the options for S are going to be S1 itself, and then all the options for S1. Okay, and that's it for this first rule. Now, for the case where S contains more than one bubble, you need to break it up into two smaller states. And you could do it any way you want. Like if you had 4 bubbles, you could break it up into 2 and 2. But the simplest way is just to say that S1 is going to be the state consisting of the first bubble, and S2 is going to be all the other bubbles. Here's how you say that. So S1 is the state just consisting of the first bubble, and S2 is everything after the first bubble. And again, this is important. The difference here between S sub 0 and S:1, this is the sort of thing that's easy to get wrong, so you definitely will want to test this function carefully. Okay, but I'm pretty sure this is right, that S sub 1 is the state consisting of the first bubble. So now we need all the options of S1 combined with S2. Okay. And all of the options of S2 combined with S1. Okay, and I think that's it. But there's definitely a chance I made a mistake, so let's test this out. Okay. Okay, so this is saying that there are 6 states that are options for S0, which is right because S0 had 6 bubbles, so there were 6 options. And this is a little confusing because Python adds this extra set of parentheses around a tuple when it prints it out. But if you ignore the outer parentheses, then you can see, looking at this, what state each of these are. So this is an empty bubble, and then a bubble containing an empty bubble. So that is equivalent to this first result here. So that's good. I think these should be in the same order, but it wouldn't be wrong if they weren't. And yeah, so these next two here correspond to these 2 states here. So that looks good. And these, yeah, these correspond to these 3 states here. And again, ignore the beginning and ending parentheses and imagine drawing a line through the state, and you should see that it matches up in each case. So this looks pretty good. So let's go ahead and try it with an actual state, an actual puzzle state here. Let's see, what's going to be the best way to do this? It's definitely going to look confusing when we type it in. So let's just take this as carefully as we can. So I could rearrange this so it's on a line, but instead I'll just draw the line that goes through every bubble. So we want to make sure we go into every bubble once and out of every bubble once. Okay, so we need to go into H, into S, through these, in and out of T, in and out of V, E, L, and then all the way out. Let's every time we enter a bubble, we'll put an open parenthesis, and every time we leave a bubble, we'll put a close parenthesis. Okay, so open, close, open, 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 close, close. All right, I think you get the hang of it. Then the end here, 1, 2, 3, 4, 5, 6 closes in a row. One, 2, 3, 4, 5, 6. So now we're going to write these down in order in the code. All right. So S0 is open, close. Okay, so we're through end. And again, every time we leave a bubble, we're going to add a comma. Open, 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 close, close. All right, so at this point, we're out of the R bubble. All right, through G. Open, 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 close, close. Okay, that gets us out of U, and all right, here's this last part. Gotta be very careful here. Oh, see, I missed one. Yeah, leaving T should have been a close parenthesis. Okay. All right, so we stopped here after leaving U. So I'm just going to follow along and type it in. Open, close, open, 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 close, 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 close. Okay, that might do it. Let's see what we get. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, great. So yeah, 13 bubbles, 13 possible next states. So that looks good. And boy, we could go through and compare each of these to another state and make sure that they all match up. And ideally we would, but I think this is probably right. Okay, so now we can solve this first puzzle pretty simply. Instead of every option, we just want the winning moves. Let's call it move. Okay, let's see if this works. All right, so there's 2 states here. I think is correct. Yeah, the first puzzle had 2 winning first moves. So looking at this, you can tell which one you popped in order to get to it. It's just kind of a pain. This looks pretty good. We got 2 out, and that's what we were hoping for. I'm also going to have it print out the size of the graph. Okay, 86. I guess maybe you could do that by hand if you had a big enough sheet of paper, but boy, this had 19 states. 86 would definitely be difficult and definitely be easy to make a mistake on. So this solution pretty much just works in a computer program. All right, so this shows the concept, shows how it's possible, but if we were really going to use this to solve the puzzle, we'd have to make this a lot easier to read. So here's what that would look like. All right, let's take a look at this example again, the 6 bubbles. So here was the state for that one. All right. So what we need to do is to extend this state with a name for each bubble so that we can determine what's left over and what's been popped at each state that you reach from here. So I think the most straightforward way to do that is to put a string as the first element of each of these, corresponding to the name of that bubble. So A goes in there, B goes in there, and like with the closed parentheses, we want to put a comma after each string just to make sure it gets counted as a tuple. So if the state's like this, then the state that you get when you pop that bubble is going to be everything after the first element. The first element's going to be the name of that bubble, and the rest of that bubble is going to be the contents of it. So this only comes into play when we open a bubble and get inside it, which is right here. So this is the state when you open a bubble, is everything after the first element. So let's try that out and see what it looks like. All right, so we're just going to look at the states that you can reach from this starting state. Okay, and so this is definitely easier to read. You can tell like what's missing, and that could help you figure out what you popped. But we can also do slightly better. We can have this function return not just the options for this state, but also what bubble do you need to pop to reach that option. Let's change the name of this popts. So now this is going to yield two things. It's going to yield the name of the bubble that you popped and the state that you're left with. So let's see. So the easy case is this one. All right, so the name is just going to be the first element of the bubble when you open it. And so we need to just add that. This is just going to be the same, except we're going to change it to the new name of the function. Whatever the name of the pop bubble is for the option of S1 that you want is the same as the overall bubble that you pop. All right, so here, this is now going to be two values, and you just want to yield the name for that. Okay, I think that should do it. So basically, when you actually open a bubble and you yield the state within that bubble, you're also going to yield that bubble's name. But when you call it recursively, whatever you popped, what was the last thing you popped when you're walking down the recursive tree, that's going to be the answer for what was the ultimate bubble that you popped. It's probably easier to see as an example, so let's just try it. Okay, so in this case it's saying if you pop A, then this is the state you're left with. If you pop B, this is the state you're left with, C, D, E, and so on. Okay, so that's going to let us identify each of the answers that are winning moves by the name of the bubble that you popped. And for this, we need to update that to ignore the name. And okay. All right, great. So now we can call winning moves, and we should get the same thing. We should get the name out as well as the resulting state. All right, so let's update this to include the names. All right, so essentially we're going to walk the same line, and every time we have an open parenthesis, we're also going to put the name of the bubble followed by a comma. So this first open parenthesis is entering the bubble N, so let's put N there. This one is entering the bubble C, then the bubble R, then the bubble A. Okay, then you leave these two, enter G, and so on. All right, I think that's the right order. All right, so the state is definitely takes up a lot more room here, but I think it's going to be easier to interpret. Okay, great. So this is saying that the bubble I and the bubble E are the two that you can pop to get a winning move. Great, so that agrees with the answer. Oh, notice that the graph size now is larger than 86. That's because now, since we've given these all names, it's going to treat, for instance, an empty bubble called G as a different state from an empty bubble called I. I don't think that's going to be a problem. I think it'll probably still run plenty fast, but if it is, there's a way we can get around that. All right, let's do one more just to make sure that we're doing this right. I'll do the second puzzle here. All right, I'm going to do the red line thing again, but I'm going to make sure that whenever I enter a bubble, I'm going to pass right through the letter. So that may mean I have to go around to the side sometimes. Okay. Okay, so I'm just going to go through and type it as I go along. I'm not going to bother writing the open and close parentheses on here. Should be able to follow it okay. So entering bubble E, entering bubble G, exiting bubble G, exiting bubble E. Okay, yeah, that is better. Thing is, like, if I had just drawn the straight line like down through this, then it'd be very tempting to say that you entered U first and then N, instead of N first then U. So even though it looks weird, having the line meander around makes it easier to not make a mistake entering it in. All right, but I still definitely could have made a mistake, so let's try this out. Okay. So this is saying there's 3 bubbles you can pop. You can pop bubble H and get this state, S get this state, C get this state to get the resulting solutions. Let's see if that's right. Okay. Yeah, great. H, S, C. So it seems like the program is correct, probably. Now that I'm confident that this is working correctly, I don't think we need to see the entire state that you move to. We could just return the letters. That's all we need to solve the puzzle. So for when moves, let's just say this is so this will just return a string that consists of the winning bubbles. Okay, cool. HSC, yeah. That's much easier to read. So that's pretty good. Okay, so before we input the rest of the puzzles, I think it might be a little nicer if we had something to sort of generate this state from a slightly shorter string. So let me see. I guess we need the name of a bubble whenever we enter one, and we need something to say that when we're exiting the bubble. All right, so I made this string here that's the same as this state here, but I only kept the names of the bubbles and the closed parentheses. And I think that I should be able to transform this back into the state representation and return an actual state. I just need to find this parsestate function. Use a lowercase s for this string. Okay, so basically I'm going to turn this string into this string and then eval it. All right, when it's a closed parenthesis, we just need to make it close parenthesis, comma. And if it's anything else, if it's a letter, then we need to make it open parenthesis, quote, letter, quote, comma. That was a little confusing to read, but so this here in parentheses is what transforms a character of this string into a couple characters in this state. All right, let's try that. Okay. I got the same result. This looks pretty good, so let's, I'm going to guess that this is correct. Then should be able to input the rest of the puzzles without too much trouble. So we'll just loop over all of them and output the winning moves for each one. I don't think it matters too much, but I'm also going to clear the cache of this function. I just want to get a good idea of what the graph size is for each individual puzzle. So I'm clearing the cache in between each one. That's obviously not necessary to solve the puzzle. I'm just curious. Need to put the first puzzle in again. Yeah, I'm not going to draw the line. I think I should be able to do it just fine by eye. 5, 6. Having line helps, but I think once you get the hang of it, you can just imagine a line. Let's see if this looks. Oops. Oh. Cache clear, not clear cache. Let's see. Okay, cool. So first puzzle, IE, graph size 284. Second puzzle, HSC, graph size 519. Okay, let's go ahead and input the other 5 puzzles. Yeah, I think the trick to these is to be systematic about it, whether it's like starting from the top and going down, and also checking your work. Yeah, I'm definitely less likely to make a mistake this way than with all those parentheses, but still absolutely possible to make a mistake. So what do you think? Does that look right? If something's wrong, the most likely thing is the program will just crash. So if that happens, we'll take it from there. Yeah, all right, here we go. Let's take another look at this one. Oh, okay, here we go. Let's try that again. Okay. Cool. So these all look reasonable. I don't know if they're exactly right. As you can see, the cache size gets up to about 40,000 here. So definitely something you'd want to use a computer program for. Let's just compare that to the answer since I've already seen it. It has the output for the program for the code that they have here. Here as well. So let's just compare. So they have EI, IE, doesn't matter the order. That's really fine. HSC, CSH. Great. So it looks like the program's correct. Let's take one more look at this program just to summarize what it looks like, because I think this is going to be very typical of a similar approach you might use if you are solving an impartial game like this in the future. First off, we have the ops function. It gives you the states you can reach in a single move from a given state. And this, I think, is generally going to be the most complicated piece of your program. In our case, we made it even more complicated by giving each move a name, which is the name of the bubble that you pop. But we had 2 rules that were both recursive that required you to call the popts function from itself. One is in the case when there's one bubble, and one is in the case when there's more than one bubble. And the results from that get combined in order to give you the overall state. All of that is super common when it comes to impartial games and similar things. And where did we get these rules? The rules came from analyzing the state and how the state behaved, and all of the different possibilities you can get from them. You're almost never going to be able to jump right in and code up your options function. Taking some time to play around with it on paper is the way to get started. So we have an isGood function, and the isGood function is implementing this rule that we had for assigning good and bad states. Basically that a state is good if at least one state among its options is bad. This is very simple, and it's the heart of the algorithm. And this function is cached so that we avoid repeating work, because this function is going to be called a lot on the same states over and over as you get down the graph. We have a winning moves function. So this looks at all the options you can get to from a starting state and gives you the name of all the winning moves. And finally, we have a parsestate function. This turns a representation of a state that's a string into something that Python can actually work with, made of nested tuples. So all of these things, the ops function, the isGood function, winning moves, parsestate, those are all going to be super common things, and it's all just a matter of writing it tailored for your specific case. But the overall structure of the program, with winning moves calling isGood recursively, and which calls options recursively, that's all very standard for solving impartial games. All right, so before we put the program aside, I'm going to time how long it takes to run. Okay, 0.6 seconds. You get the output for this, and that, of course, is absolutely fine. If you were trying to solve this for Mystery Hunt, less than a second there's no point trying to make it any faster. But this can be solved faster, and that's what we're going to look at next. Okay, and just so we have the complete solution to the puzzle in the video, let's go over what you do once you get the winning moves. I'm going to open up the 7 puzzle images on top of each other. You need to be able to see through them. All right, great. Mm-hmm. All right, let's go through each of these and circle the winning move bubbles. I remember for the first puzzle it was I and E. Puzzle 2 was H, S, and C. Right. All right. Now let's look at them all together again. Okay, I'm supposed to read them across like this. Yeah, if you can't see that very well, it's ANSWER RELIE FPITCHER. So answer relief pitcher. So that's all you had to do. All right, let's go back to the beginning. To review, you remember we had this board game where players take turns moving the token around, and we analyze the board game by assigning every space in the board game one of 2 designations, good state or bad state, using this rule. So the next step is very similar. We're going to analyze the board game again using a slightly different technique, one that will turn out to be more powerful. And if you recall, every impartial game is equivalent to a board game like this because the squares represent states of the game. So this technique will also apply to every impartial game. So this technique involves assigning every state, every square in this game, a number, 0, 1, 2, 3, etc. And to choose the number, we're going to use a function called mex, which I will define in just a minute, but let me give some examples first. So first of all, any square that has no outgoing squares that you can't make any moves from gets a number of 0. And that is because the mex of nothing is equal to 0. Now, if a state only has one output and that output is 0, that state gets a number of 1. And the same with this one, because this one points at 2 outputs and they're both 0. That also gets a number of 1. Here has one output that's 0, that gets a number of 1. And that is because the mex of 0 is 1. Okay, how about this state here? This state has 2 outputs. One has a number of 0, one has a number of 1. So the value for this state is going to be the mix of 0 and 1, which is equal to 2. This state here has two outputs, and both of them have a number of 1. So the value for this state is going to be mix of 1, which is 0. Okay, if you haven't guessed the rule yet, the rule is MEX stands for minimum excluded. It's the smallest number that does not appear in this set. So in every case, we want the smallest number that you cannot reach from that state. So from this state, you can reach states with values of 0 and 1. And as we said, the MEX of 0 and 1 is 2. So this one gets a value of 2. This one as well, 0 and 1, value of 2. This one as well, 0 and 1, value of 2. So from this state, you can reach states with values 2, 2, or 0. So we want the minimum excluded value from 0 or 2. So the smallest number that does not appear here is 1. So that's a 1. All right, this state has 4 outputs, and they have values of 2, 1, 1, and 2. So the smallest number that does not appear in there is 0. Okay, and that just leaves the starting state. From here you can reach states of value 2, 0, 1, or 2. Two, 0, 1, or 2. Okay, and so the smallest value that does not appear in here is 3. Okay. All right, so we have these numbers. So what does that tell us? Well, for one thing, it tells us which states are good states and which states are bad states. Look carefully at the bad states, these 4 x's here, and look at their values. They're all zeros. And every state that was a good state is something that's not 0. 1, 2, 3. Anything higher than that is going to be a good state. So this number, first of all, tells us which states are bad states and which states are good states by seeing whether it's 0 or not. So let's go ahead and add it to our definitions now. So if a state is a good state and a first player win, a blue circle, then this state has the value n greater than 0. And the state's a bad state, and it's a second player win, then this state has the value n equal to 0. And let's also give the definition of n itself. So n is called a nimber, and of course it's named after the game of Nim, the most famous of impartial games. And it's also called a nim sum or a Grundy value. I've heard it called Nimber the most, so that's what I'll be calling it. The formula is n of a state is equal to the MEX of the n of all of the ops for that state. So the nimber is the MEX of all of the nimbers of the states you can reach from that state. And let's also include the definition of the MEX function here. MEX is short for minimum excluded. So it's the smallest value that is not in the set. Okay, great. So with this definition, we could define the nimber for every state in a graph of an impartial game. All right, so that's pretty good, but the real power of the nimber will become clearer if we actually use it to analyze a game of Nim. All right, so do you remember this graph? This was what we used to analyze the example game from the puzzle that consisted of 1, 1, 2, and 3 concentric bubbles in the starting state. All right, so 1, 1, 2, 3 is the starting state, and these are all the intermediate states. So we can do the same thing here. We can assign a nimber to each of these states. And I don't know if you remember, but I said that this is equivalent to a game of Nim, where you have stacks of size 1, 1, 2, and 3, and you can pull as many as you want from a single stack. If you'd rather think of it in terms of the bubbles, that's fine too. It's equivalent. But remember that this can't represent every bubbly game, only the ones where you have some set of concentric circles. All right, let's just get started. So this state here that you cannot reach any other states from, of course, gets a number of 0. This state that you can only reach a state with a number of 0 from gets a number of 1. All right, from this state you can reach 0 or 1, so this gets a 2. This state can only reach 1, so that gets a 0. Okay, just to be a little more explicit about what I'm doing, so for every state here, I'm putting the nimber of that state above it, and below it I'm going to put the nimber of all of the options of that state. So I'll put these in orange below it. All right, so this one doesn't have any options, so there's nothing there. This one only has an option of 0. This one has an option of 0 or 1. This one only has an option of 1. Okay, this one has options of 0, 1, or 2. This one has options of 2, 1, or 0. Okay, so to be clear, the pink numbers from each of these states are becoming the orange numbers in the state you can reach that from. So 0, 1, or 2. And this one only has 0. And then the pink numbers for each state is just going to be the smallest number not included in the orange numbers. 3, 1, 0, 3. 3, 1, 0, 3. 2 or 3. 0, 1. All right, 3, 2, 2, 3, 0. 3, 2, 2, 3, 0. 2, 0, 1, 2. 0, 3, 2. This one has 6 options. 1, 2, 3, 3, 2, 1. 1, 2, 3, 3, 2, 1. 3, 1, 0, 3. All right, and finally from the starting state, you can reach states with a number of 0, 3, 2, 2, 3, 0. And so that gets a number of 1. Okay, I think that's probably right. One thing to check is that the ones that had a red X before, when we were doing the good state, bad state analysis, all wind up with a number of 0. Yep, 0, 0, 0. And the ones that are blue are all non-zero. Cool, great. So that's good, but there's more patterns than just that. All right, I just want to make this a little easier to read. So I'm going to just copy over the name of the state and the nimber. Okay, here's all the states and their corresponding nimber. So take a look at this and see if you can see some patterns. So one that should be pretty clear is that when the state consists of just one number, the nimber is equal to that number. Okay, and you can imagine if you had a single state consisting of the number 7, then the nimber would be 7. That's always going to be true. You might also notice that the same value seems to cancel out. So if you have 2 and 2, that cancels out to get 0, and this 2 and 2 cancels out and you're left with just 1. In this case, the 1's cancel out and the 2's cancel out and you're left with 0. Yeah, so 2 1's cancel out, you're left with 1. So, and that's always going to be true too. If you have 2 of the same numbers, you can ignore them and just, it's always going to be what's left over. So the ones that aren't immediately clear are this one. 1 and 2 is 3. Yeah, that's true. But you don't just add them together. For instance, 2 and 3 makes 1, not 5. And 1 and 3 makes 2, not 4. So is there a pattern here that will always tell you what the nimber is for a state without having to draw the whole graph? And the answer is yes. All right, here it is. So as an example, the nimber of state 1, 1, 2, 3 is equal to 1 plus 1 plus 2 plus 3. And this circled plus sign is known as nimber addition, also known as exclusive OR XOR. Okay, so what is nimber addition? So the rules for nimber addition are split into distinct powers of 2 and shared powers of 2 cancel out. And the powers of 2 are 1, 2, 4, 8, 16, and so on. All right, let's look at an example. Split into distinct powers of 2. So let's take 14. You can always split any number to different powers of 2. So in this case, it's 8 plus 4 plus 2. 11. 11 is 8 plus 2 plus 1. And now shared powers of 2 cancel out. So the shared powers of 2 here are 8 and 2. So those cancel out, and we're left with any power of 2 that only appears in one or the other. So 4 plus 1. And this is 5. 14 XOR 11 equals 5. So I suspect that a lot of you knew this. This is probably the most famous fact when it comes to impartial games. But whether you know it or not, it does take a little getting used to working with this. So let's look at a little more detail. One thing that might or might not be obvious is that every number is going to cancel out. You remember when we saw numbers canceling out? So any number added to itself this way is going to come out to 0. So 27 XOR 27 equals 0. Let's see, some simple examples are 1 XOR 2 equals 3. We saw examples of all of these. Okay, so you see how the numbers sort of can go anywhere in here? That's always going to be true. So if you have, another example would be 3, 5, and 6. You can put them anywhere in this equation and it's still going to be true. All right, so that's pretty handy. And just to show this in a little more detail, 3 equals 2 plus 1, splitting into powers of 2. 5 equals 4 plus 1. And 6 equals 4 plus 2. So if you add 3 plus 5, the 1's cancel out and you're left with 4 plus 2. If you took 5 plus 6, the 4's cancel out and you're left with 2 plus 1. So it's always going to work out. When you have a series like this, you just take them one at a time, one pair at a time. 1 XOR 1, XOR 2, XOR 3. There's a bunch of ways you can do this quickly in your head. The 1's are going to cancel out, so that's 0, XOR 2, XOR 3. Anything XOR with 0 is just going to be that number itself, so that's 2, XOR 3, which is 1. You could also have done this easily another way by noticing that 1, 2, and 3 are going to cancel out. 1, so you just have 1 plus 0. Yeah, it's definitely weird, but you get the hang of it. You don't have to memorize all these examples. You can always split it out and do it in terms of powers of 2. You can look up there's a Nimber addition table. So you can see like 3 plus 5 gives you 6 here. If you mess around, like I can pretty much do everything up to 7 in my head, and we mostly deal with small numbers. That's going to cover most of the times. But you can see that if you can do this quickly in your head, then it's very easy to win a game of Nim, because you can quickly figure out what is going to be the Nimber of the states that you can put your opponent in, and choose one that has a Nimber of 0. So in this case, starting state had 1, 1, 2, and 3, and Blanche put her opponent into a state with 1, 2, and 3, which 1 XOR 2 XOR 3 is 0. The other option Blanche had is popping the E bubble, and that would put it in the state 1, 1, 2, 2. And again, the 1's cancel out, the 2's cancel out. So that one also has a Nimber of 0. So you see, in order to win, Blanche did not have to analyze this entire graph. She just had to look one step ahead at each of the options from the starting state and see their Nimbers using the formula for Nimber addition. Okay, so one thing you might be wondering is, where did this formula come from? Can you prove it? And there is a pretty short proof, but it's not super clear to me. I don't find that it really helps me understand why this is the case. So I'm not going to go into the proof. It's on Wikipedia. So we're just going to use this result without proving it. All right, let me just add this definition here. So this symbol means Nimber addition, exclusive OR. So with that, the game of Nim is pretty much solved. Any Nim game you have, or Bubbly state that is equivalent to a Nim game, you can almost do in your head. You can certainly do it on paper. So if the puzzles we had were all equivalent to Nim games, then we could solve this pretty quickly. But they're not, because we have some bubbles that contain more than one bubble. So the next thing to look at is, can we find another way to get the Nimbers of Bubbly states efficiently without having to construct the entire graph? Okay, if we want to figure out how to get the Nimbers for general Bubbly states, let's start by looking at a few examples. All right, so first of all, we already know a few of them. So if you just have a single bubble, or a single bubble within another bubble, or, if we had 4 concentric bubbles. All right, so then it's just going to be the number of bubbles. 1, 2, 4. And if we have a set that's made up of concentric bubbles like this, we also know how to handle these. So let's look at these examples. Alright, so in each case we just use Nimber addition on the individual values. Okay, so those are very simple examples that we'll need to keep in mind because more complicated states are going to be made up of these. Alright, so the simplest state that doesn't fall into one of these categories is going to be 2 bubbles and 1 bubble containing both of them. So in general, whenever we have a state that we don't already know how to get the Nimber of, we can always find it using the definition here. So we just need to figure out all the options for this state. So you can pop the outer bubble and get this state, or you can pop the outer bubble and one of the inner bubbles and get this state. Now, of course, we know the Nimbers for these states. That's 0 and 1. The minimum excluded value from this is going to be 2. So the Nimber of this state is 2. All right, how about this one? Again, we can just write out all the possible states you can reach from it. Pop the left bubble, you just get 2. All right, 4 possibilities. All right, we know the Nimber for each of these. 1x or 2 is 3. 2, 0, and 1. These are the Nimbers of the options. So the Nimbers of the options are 0, 1, 2, and 3, and so the minimum excluded value is 4. Let's do one more like this quickly. Zero, 3, 2. So from here you can reach states of 0, 3, or 2, and so this one gets a Nimber of 1. Okay, another state we don't have covered yet. All right, what about this? A bubble that contains 2 empty bubbles and an empty bubble. Okay, pop the outer bubble. Get that. Pop the outer bubble and one inner one, you get that. Pop the small one, you get that. Okay, so that's 1x or 1x or 1 is 1. 0. And this one we did up here as Nimber of 2. 0, 1, 2. Now let's do one more like this. Okay, 1 bubble containing 2 empty bubbles, 1 bubble containing 1 empty bubble. There's a lot of possibilities here. Or you could pop both of these. Okay, so we know all of these. 1x or 1, x or 2 is 2. 1x or 2 is 3. This one we did here, it's 3. And this one we did here, it's 2. Alright, so 2 or 3. This one gets a Nimber of 0. Alright, did you see that coming? So I think when you get a problem like this, it's good to look at the small states that you can analyze completely, so that you can find a formula that generalizes like we have with nim. And remember, we can't do most states this simply. Don't forget why we're doing this. Like if we have some general state here, so this has 9 bubbles. So at most there would be 9 states that you can reach from here. So you might think, oh, we could just do it quickly. I mean, this is only 9. But remember, it's not going to be that simple. Because for instance, one of the states, if you pop the bubble on the left, you're going to have a state that looks like this. And we don't know the Nimber for this state. It's not anything we've analyzed before. So in order to get the Nimber for this, we have to find out everywhere you can get to from here. Like if you pop this first bubble here, you get to another state. And we don't know the Nimber for this state, so in order to get that state's Nimber, we have to keep going. And remember, so this one has 9. Or this one might have a bunch as well. And so, in general, it's not just a number of places you can reach from it. So we're looking at these simple states so that we can come up with something that lets us handle the more complicated states without building the entire tree that they're based on. Okay, if there is a pattern here, it's not obvious to me, but there is one thing that helps us a lot. The Sprague-Grundy Theorem. I think that's how you say it. I'm not sure though. So this is a very important theorem in Nimber analysis, and I'll write out what it means in terms of Bubbly, and then I'll explain it. Okay, so the Sprague-Grundy theorem says that the nimber of a state that's equal to S1 plus S2 is equal to the nimber of S1 XOR the nimber of S2. So basically this is saying that you can use nimber addition in any impartial game, even if it's not equivalent to a nim game. So of course we should look at an example. All right, let's say this state here so the bubble on the left that contains two smaller bubbles is S1, and the bubble on the right that contains one smaller bubble is S2, and S, the entire state, consists of both of them together. Now, we know, because we worked it out, that the nimber of S1 is 2. Okay, and the nimber of S2 we know is 2. That's one of the easy states. Okay. So the Sprague-Grundy theorem tells us that the nimber of the combined state S1 plus S2, 2 XOR 2 is equal to 0. Okay. So we didn't have to look at every possible move from here because we knew the nimbers of the two states that make it up. We can get that at 0. Yeah, we actually looked at this state earlier, right here. Yeah, so it agrees with what we found earlier, that this state has a nimber of 0. Let's take a more complicated example. I'm going to write down a couple of states that we already know the nimbers of. Okay, these two we analyzed just a minute ago. They have numbers of 2 and 4. And this one obviously has a number of 3. The state here, Sprague-Grundy tells us that it's just the nim sum of each of the individual ones. And that's 2 and 4 is 6, 6 and 3 is 5. All right. Okay, so I think that's pretty cool. So for instance, you could put together any 3 bubbly states, and if one has a number of 2, one has a number of 4, one has a number of 3, then their combined state will always have a number of 5. And that's not at all intuitive to me. I can pretty much understand it when they're equivalent to nim stacks, because nim stacks are very simple. But you can imagine some really complicated bubbly states. But as long as it has a number of 4, you can swap it out for this state and you'll get the same result. Cool, so it's neat and it's also very powerful. This lets us quickly get the number of any state as long as we have the number of everything that makes it up. Fortunately, that's not everything we need. All right. Just as an example, let's say I took this state that we know has a number of 5, and I drew another circle around it. So here's a new state, and we'd like to know what its number is. So Sprague-Grundy does not help us here. We cannot break this state up into 2 independent states. It'd be great if there was formula like the number of a state surrounded by a bubble is equal to the number of that state plus 1. Yeah, this is not true. I tried for a while to find a formula like this, but I was unsuccessful. So here's a simple example of the issue you run into. So this state here, inside the bubble, has a number of 1 XOR 1, which is 0. So this is a bubble surrounding a state of 0. And so is this one. This inner state has a number of 2 XOR 2, which is also 0. So this is a bubble surrounding a nim state of 0. But this one has a number of 2, this one has a number of 1. So you obviously can't do it just in terms of that. So there's not going to be a general formula for the nimber of a state surrounded by a bubble just in terms of that state's nimber. Now is, I think, a good time to look at the solution. So the solution of the puzzle came with this program that solves it, and it uses a lot of the concepts we've been talking about. A lot of this program looks very similar to the one we wrote earlier. But before, when we were just using good states and bad states, they're actually computing the nimber. And then they compare the nimber to 0 to see whether it's a good state or a bad state. All right, so let's take a look at how they do it. All right, I'm not going to explain every line of code here, but this block here is the Sprague-Grundy Theorem. L is the set of bubbles that make up the state. So if there's more than one bubble, more than one independent subgame, return XOR of subgame nimbers. So then it just calls recursively nimber on each of the individual bubbles, and this caret is the Python symbol for XOR. So it just XORs them together, and that's how it gets the number for this state. That's great. But here's how they handle when there is only one bubble. Okay? I was hoping to find just as simple of a formula. So what they do in this case is they fall back to the original definition, where you find the nimbers of all of the options and then take the max of that. So this is looping over the entire state and looking for every bubble. It pops that bubble and takes the resulting state and takes its nimber, and which is the same thing as we were doing here. And this line takes the max of that, finds the smallest number that is not in num set. So this works, and it works fast. I compared the run times. I don't know if you remember. So this is my program, and it took 0.6 seconds to run. This is the program from the Puzzle Solutions output, and it took 0.06 seconds to run. So obviously much faster. It doesn't make a difference as far as solving the puzzle goes. Either one of them is fast enough, but it's cool that it uses this more sophisticated technique and gets a 10 times faster runtime. The original output from the program looks like this. I modified it because I was curious about how big the graph is that they have to make. Because they're doing a sort of intermediate optimization here, where if there's just one bubble, then they do have to explore the tree, but if there's more than one, then they get a big improvement. So here's all the cache sizes. This is the number of different states they had to compute the nimber for each one, and the highest is only 62, which is way better than 40,000, which was what my program did. So that's really good, but I think that it's probably still a little too complicated to do by hand. I mean, 62 is not bad, but I mean, some of these states get really complicated. Like in this one on the very first move, since it's just a single bubble, you have to find all the options for this bubble, and there's 21 letters, so there's 21 different options for popping this. So this state's going to have like 21 arrows pointing out of it. Like in this case, the most we had coming out of one of these was 6 arrows, I think. So I'm sure that if you were really careful, you could do it by hand, but I think it would be very easy to make a mistake analyzing something like this. Okay. Before we get to what we're going to do about that, let's update our program to use everything we've learned about nimbers. All right, let's say this is bubbly-n.py. So the basic thing we need to do is replace the isGood function with a function that gives you the nimber of a state. Okay. And for this, we are going to go to our definition. So to start, we're just going to not use the Sprague-Grundy theorem. We're just going to use this definition here. So the mechs of the nimbers of each of the options. Okay. Actually, let's make this a set. And for the mechs function, so this is the smallest value that's not in the set. I'm going to need the count function for this. Okay. All right, so this is just going to count up 0, 1, 2, check whether each of the values is in the given value set, and if not, then as soon as it finds one, it returns it. Okay, and winning moves needs to be updated. Remember, our definition of whether a state is winning or not is it's bad if n equals 0. So we'll replace this with -1 equals 0. I think that's about it. Since we changed the name of the function, I'm just going to print out the cache size of this function. Let's give that a try. All right, looks like it's giving the right output here. The numbers are a little bit bigger, but not much bigger. And it looks like the program, instead of taking 0.6 seconds, took 1.4 seconds. So over twice as long. So obviously, changing to nimbers by itself didn't help us. But now let's apply the Sprague-Grundy theorem. Okay, so if the two more independent states, then we can split them up and take the XOR of the individual numbers. All right, so just like we did in popts, we'll check if the length of S is greater than 1. And then if it is, then we'll break it into these two smaller states. Okay, and we want to return Nimber of S1 XOR the Nimber of S2. And this caret is the Python symbol for XOR. And hopefully that improves the runtime. Okay, great. So yeah, same output as before, and you see it's at 0.05 seconds. You know, a really big improvement. And the graph sizes are much smaller than they were before. They got up to 40,000 before. These are much closer to the given solutions cache sizes. Theirs is a little bit smaller because they have one more optimization I won't get into. You can see why it runs so much faster, because the number of states that it's checking is so much smaller. Back to the problem we still have. So we have some state S, and we're doing this by induction, so we assume that we know the number of S, say it's 3, and we have a state that consists of S inside a bubble. And we want to know, what is that state's number? So we know that just the number of S is not enough, because we've seen examples where this is 0 and this is 1, or this is 0 and this is 2. So how much else do we need to know about S before we can get this number here? And the answer is we need to know the orange numbers too. So let's see why that is. Make a copy here. So we can't say, based on this, what the number of this state is. Can we say anything about this, the number of this state? Well, yeah, we can say a couple things. First of all, if you just pop the outer bubble of this state, then you get to the state S, which means that state S is an option of this state, which means that the 3 will also be one of the orange numbers here. So that means that the number of this state cannot be 3. What about the other states that you can reach from this state? Well, we've figured that out before. Yeah, here's the rule. I'll copy it over. The options of this state consist of S itself and everything you can get to from S. All right, so, in general, that could be anything, but let's just depict it here. Yeah, there might be some other states here. And these are the options of S. Because you can, while you're popping the outer bubble, also pop any bubble within S, all these options are also available to the upper state here. And remember that the nimbers of these states, let's say there's a 1 here, are going to appear in the orange values for S and also in this one here. So in general, the orange numbers for this state are going to be the orange numbers for S plus the nimber for S. So let's do an example. Let's say the nimbers of these 4 states are 1, 5, 0, 2. Okay, so 0, 1, 2, 5. And remember that at least 0, 1, and 2 are going to have to be in here because the nimber of S has to be the smallest value that's not in here. So 0, 1, and 2 have to be in this if the nimber is 3. But that means that 0, 1, 2, and 5 are also going to be orange numbers here. And that is enough for us to get the nimber of this state, 4 in this case. If this had been 0, 1, 2, 4, then the orange numbers here would have been 0, 1, 2, 3, 4, and this would have been a 5. All right, so that's the rule. That's how we get the nimber of any state that's just a state we already know is surrounded by a bubble. We could have gotten that from the formula here. I'll go ahead and write it out as a formula. Let me add a definition. Just to be clear. I'm not going to give this formula a special name just because it's so simple. But I'm just going to write out what the orange number means. Alright, so I'm just using nops as shorthand for n of ops. That means you can also write this in terms of nops. Okay. The orange numbers are the pink numbers of the options, and the pink number of a state is the smallest value not included in the orange numbers for that state. All right. So we can write this rule just by taking n of both sides here. On the left side is just going to be nops. So the orange numbers for state contained by a bubble is equal to n of this side, so the pink number of that state, and the orange numbers of that state. Okay, great. So this formula gets us a lot of the way there. But that means that in addition to keeping track of the pink numbers for all the states, we'll need to keep track of all the orange numbers. Okay, we're getting close. Let's start putting it all together. We have almost everything we need to get the nimber of any bubbly state recursively in terms of the nimbers and the number of the options of the states that make it up. So let's review what we have. This formula for the orange numbers of a state that's a single bubble. Of course, we can also get the pink number for this state in terms of the orange number, so I'll write that in. All right. As with any state, the pink number is just the smallest value not included in the orange numbers. Of course, the Sprague-Grundy Theorem gives us the pink number for any state made up of two independent states. But of course, we also need the orange number for a state like this. We'll need it in case it's enclosed in a bubble like this. Okay, and so that's the one we still need to get. But once we have that, we'll have everything we need. The only state that's not going to be one of these two cases is the empty state, and that's completely trivial, but I'll write that in just for completeness. The pink number for the empty state is, of course, 0, since it's a bad state. And the set of orange numbers for the empty state is the empty set, because there's no options from the empty state. All right, so that is everything. Once you have this formula, this will be complete. We'll be able to get the Nimber for any state. Okay, nopts of S1 plus S2. For this, we're going to go all the way back to this page where we found the ops of S1 plus S2, back when we were doing the good state, bad state analysis. So we can get it by taking n of both sides of this equation and applying the Sprague-Grundy theorem. But let's talk about what that's going to mean first. Now, you remember on this page we had this example of a state that is made of two independent states, S1 and S2. And we got the ops for the combined state by taking the ops for the individual states and combining them the right way. So each of the ops for S1 gets combined with S2 to make these options for the combined state. And that's this part of the equation. And each of the options for S2 gets combined with S1 to make these options for the combined state. And that's this part of the equation. All right, so now let's look at this in terms of nimbers. All right, let's just fill in the nimbers for these. We've done these before, so this is a 2, this is a 3. Each of these is 0. All right, so we know the number for S is going to be 2 XOR 3, which is 1. And our goal is to get the orange numbers for the combined state. So we have the orange numbers for S1 and S2. That's just the pink numbers for their options. So for S1, it's 0 and 1. And for S2, it's 0, 1, and 2. I'm going to leave the commas off from now on, just because we're going to be doing a lot of these. So the orange numbers for S are equal to the pink numbers for each of the options. So what are each of these options? Well, this first one is a combined state. And on the left here, we have this state BC, which has a pink number of 0, combined with S2, which has a pink number of 3. So using Sprague-Grundy, we can say that the Nimber for this state is 0 XOR 3, which is 3. Okay, and here, this state has a number of 1, this state has a number of 3, so the combined state has a number of 1 XOR 3, which is 2. And same with this one, also 2. In this case, we have S1, which has a number of 2, combined with this, which has a number of 2. 2 XOR 2 is 0. 2 XOR 1 is 3. And 2 XOR 0 is 2. So these are the pink numbers for the options of S. So that lets us write the orange numbers for S. 0, 2, and 3. And fortunately, the pink number for S is equal to the smallest value not included in this. So that's the basic idea. I'm going to add a little table here, just as another way of showing what we did. All right, so first of all, we just combine the pink numbers. 2 XOR 3 is 1 to get the pink number for S. And then to get the orange numbers for S, we combine the orange numbers for S1 with the pink number for S2, and the pink number for S1 with the orange numbers for S2. And so that corresponds to joining up each of the options from S1 with the options of S2. So this is great. So we don't need to actually write out the options for anything like this in order to get the orange numbers for a combined state. We just need to combine the orange and pink numbers in the right way. All right, so let's just take n of both sides of this equation in order to see the same thing in terms of the formula. So n of the left side is just this value, which is what we're trying to find. If we take n of the right side, then we have n of ops S1 plus S2, and by the Sprague-Grundy Theorem, that's n of ops S1 XOR n of S2. Okay, so that's just n of this value here. And n of this value here is just n of S1 XOR n ops of S2. So this formula is just saying to get the orange numbers of the combined state, we take the orange numbers of state 1 with the pink numbers of state 2 and combine them with the pink numbers of state 1 with the orange numbers of state 2. So we can add this to our list of formulas here. Now this list of formulas is complete. Okay, so this is everything we need to solve the puzzles. Before we do that, let's just do one more quick example. Here's a good one. So this, we saw this earlier when we were looking at the pink numbers for a combined state. This is something we mentioned under the Sprague-Grundy Theorem as a state we could not get the nimber of, but we can get it now. So we have these three states that we know the nimbers of, and we combine them and use Sprague-Grundy to get the nimber of this state. But we said at the time we could not get the nimber of that state surrounded by another bubble. So now let's apply a rule. First of all, in good recursive fashion, we assume that these smaller problems are already complete. So I'll just put in the orange numbers for these states. Let's give these some names. So in case it wasn't obvious, the XOR function is very well behaved. It's associative, commutative, all those good things. So you can easily extend this to 3 or more bubbles, just the way you would think to do it. So we could do this all in one step, but an alternative is we could break this down into 2 smaller states, one consisting of S1 plus S2, and one consisting of just S3, and then break down the first state into 2 smaller states and apply it again. So that's what we'll do. Let's make a table here. All right, then this combined state will be combined with S3. That will give us S. Two, 4. So S1 plus S2, just these 2 bubbles together. So of course, the nimber for this will be 2 XOR 4, which is 6. And the orange numbers will be 0 XOR 4, which is 4. 1 XOR 4, which is 5. 2 XOR 0, which is 2. 2 XOR 1, which is 3. 2 XOR 2, which is 0. And 2 XOR 3, which is 1. Okay, so 0, 1, 2, 3, 4, 5. Great. So now we do the same thing with this state and S3 to get the numbers for S. Of course, 6 XOR 3 is 5. Which is good, that's what we already had. 4 XOR 3 is 7. 5 XOR 3 is 6. 2 XOR 3 is 1. 3 XOR 3 is 0. 0 XOR 3 is 3. 1 XOR 3 is 2. 6 XOR 0 is 6. We already have that. 6 XOR 1 is 7. And 6 XOR 2 is 4. So 0, 1, 2, 3, 4, 6, 7 are the orange numbers for S. And now to get the orange numbers for this state, it's just the pink numbers for S and the orange numbers for S combined. So we just add 5 into here, so it's 0, 1, 2, 3, 4, 5, 6, 7. Okay, and of course, to get the pink number for this, we just take the mex of the orange numbers, which is 8. Okay, that's all there is to it. Hope that this process is not too bad because we're going to be doing a lot of it when it comes to actually solving the puzzles. Let's start with one of these puzzles here. Okay, so for each of these bubbles, let's figure out what the nimber of the state consisting of just that bubble is, that bubble and its contents. All right, we'll start with an easy one. N has a nimber of 1. It's equivalent to a nim stack of 1. The only option if you pop it is the empty state. So its orange numbers are 0. Very simple. Same with A here. And same with G here. Now R only contains A. So according to our rule here, the nimbers of R are the pink and orange numbers of A, 0 and 1. So its nimber is 2. So we could also just say that R is equivalent to a nim stack of 2. And that's probably going to be simpler in general. So for instance, U here is equivalent to a nim stack of 2. I is 1, T is 1, L is 1, E is 2, V is 3. And so we don't need to put the orange numbers for the inner states here. Yeah, the only reason we would need the orange numbers for E and L is to figure out the orange numbers for V. So we can just put V as 0, 1, 2. So anytime I have one that's just a nim stack equivalent, I'll just do the outermost one. All right, great. So that is the trivial ones. Now we've got S. So the state S is a bubble around the state consisting of U, T, and V. So I'll make a table like we had before. U, T, U plus T, V, U plus T plus V, and then S. Yeah, which is a bubble around this state. T is 1, V is 3. So U plus T, the number is 2 XOR 1 is 3. And the orange numbers are this pink with this orange, this pink with these oranges. So as a shortcut here, I know there's only going to be 3 values here because it's one value with this one and one value with these two. And I know that at least 0, 1, and 2 have to be here because 3 has to be the smallest value that's not in here. So I know this is going to be 0, 1, 2. I could work it out, but this is a convenient shortcut. But in this case, I do have to work it out. So 3 XOR 3 is 0. 3 XOR 0 is 3. 3 XOR 1 is 2. 3 XOR 2 is 1. And I don't do the other way because it's going to come out to the same things. So now, since S is a bubble around this state, I take the pink and orange numbers, 0, 1, 2, 3, and that gives me S's number, which is 4. Copy that over. Right, so H is just a single bubble around S, so H's orange numbers are S's pink and orange numbers, 0, 1, 2, 3, 4, and this pink number is 5. Okay. So for C, C contains 3 bubbles, so we'll make another table here. G, R, and H. So G is 1, R is 2, and H is 5. And their orange numbers are just everything up to those values. Okay, 1 XOR 2 is 3. Same trick as before, there's only 3 values here, so I know this will just be 0, 1, 2. Alright, 3 XOR 5 is 6. So 0 XOR 5 is 5. 1 XOR 5 is 4. 2 XOR 5 is 7. 3 XOR 0 is 3. 3 XOR 1 is 2. 3 XOR 2 is 1, 3 XOR 3 is 0, 3 XOR 4 is 7, we already have it. Okay, great, so 0, 1, 2, 3, 4, 5, 7, and the pink number is 6. So that's the state consisting of G, R, and H together. C wraps that in another bubble, so C's orange numbers are going to be these numbers, so 0, 1, 2, 3, 4, 5, 6, 7. And so C's number is going to be 8. Great. One last state we need is the state consisting of the entire thing. So that's just 1 XOR 8, which is 9. Let's put it up here. We could get the orange numbers for this state, but we don't need them. The only reason we ever need orange numbers is to get the pink numbers for higher states, so we can stop here. Great, we don't need the orange numbers anymore. We can just work with the nimbers for all these bubbles. We know that this overall starting state has a number of 9, which means that this is a good state, a first player win, which means that there is at least one move that will result in a state with a number of 0. So now we have to find out what those moves are that will result in a number of 0. Just to be explicit, I'm going to write that out here. Write out here how we're going to designate that. We have some bubble named B, let's say. But what exactly do we mean by the nimber of bubble B? So I'll just write it out here. So the pink numbers that we have are the nimber of the state consisting of just bubble B and its contents. But that doesn't tell us what the winning moves are. So for that, we'll use a different color. All right, I haven't used this light blue yet. And let's put this at the bottom left. Call this P. And here's what we mean by the blue number. Okay, so pink number N is the number of the state consisting of just bubble B and its contents, and the blue number P is the number of the state you get if you pop bubble B from the starting state. So if P is 0, that means that when you pop bubble B, you get to a bad state, which means that that is a winning first move, and that's what we want. So how do we find P from these? Let's start with just the simplest way. The simplest way is just to look at what's left over when you pop that bubble and just XOR all of those bubbles together. So if you pop N, you're left with C. And C has a number of 8, so the blue number for N is 8. Okay, now let's work from the outside and go in. So if you pop bubble C, you are left with N, R, G, and H. So the number there is 1 XOR 2, XOR 1, XOR 5. If you don't have enough practice doing XORs by now, this isn't too bad to do in your head. The 1s are going to cancel out. 2 and 5 gives you 7. So now we just do all the bubbles in the same way. If you pop a bubble R, you're left with N, A, G, H, 1, 1, 1, 5, gives you 4. And if you pop bubble A, you're left with 1, 1, 5, which gives you 5. Okay, pop G, you're left with 1, 2, 5, that's 6. If you pop H, you're left with 1, 2, 1, 4, because S is still there. That's 6. If you pop S, you're left with 1, 2, 1, 2, 1, 3. Yeah, 1, 2, 1, 2, 1, 3. 2 of the 1s cancel and the 2s cancel. So you're left with 1 XOR 3, which is 2. All right, great. U leaves you with 1, 2, 1, 1, 1, 3, which is 1. I leaves you with 1, 2, 1, 1, 3. 1, 2, 1, 1, 3. So the 1s cancel, 2, 1, 3, those cancel, it gives you 0. Okay, so that means that I is a winning first move because you're left with a state with a nimber of 0. Let's see. T leaves you with 1, 2, 1, 2, 3. That's 3. V leaves you with 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2. 3. E, if you pop bubble E, you're left with 1, 2, 1, 2, 1, 1. 1, 2, 1, 2, 1, 1. So that's 2 2s, which cancel, and 4 1s, which all cancel. So 0. And L is the same, except that one of the 1s is missing, so that leaves you with 1. Now you have 2 2s and 3 1s. Okay, great. So that solves this puzzle. We just take the bubbles that have blue numbers of 0. That's I and E. Popping I leaves you with a number of 0. Popping E leaves you with a number of 0. Okay? Now remember, that is correct. Okay, so that works pretty well, and we could do it with the other 6. I think it would be slightly easier if we rewrote the state. Let's go ahead and look at the next one. So I'm just going to represent this state a different way. And the way I'm going to do it is put all these letters into a graph structure, and whenever a bubble contains another one, I'll just put it below it. So for instance, E contains G. HVPR. All right, and I, on the one hand, contains F, which itself contains S, and N, which contains U. And on the other hand, I contains T, C, A, L. Great. So I think this will be slightly easier to work with. Let's start with the simple nimbers. Yep. Anytime it's a stack like this, it's just a nim stack. So just put the numbers up like this. 1, 1, 2. All right, great. We just got 2 more we need to solve. We don't need the orange numbers for anything that's below something we've already solved. Okay, great. So now we need to get F. So I'll write off to the side here the state S plus N. So this has a number of 1 XOR 2, which is 3. And oh, yeah, okay, because there's only 3 combinations here, I know this is going to be 0, 1, 2. So F's orange numbers, since F contains this state, it's going to be 0, 1, 2, 3. And F is 4. I feel like we've seen this arrangement before, so if we see this again, we can remember that this arrangement is just 4 and 0, 1, 2, 3 here. It's just like a nim stack of 4. Okay, now let's do F plus T. All right, 4 XOR 4 is 0. And the orange numbers, it's 4 XORed with 0, 1, 2, and 3, which is 4, 5, 6, and 7. Now, of course, since I contains this state, I gets orange numbers of 0, 4, 5, 6, and 7, making I's number 1. Cool. Yeah, I do feel like this is easier to work with than the bubbles. So now, let's get the blue numbers. So if you pop E, you get G, H, and I. Their numbers are 1, 4, and 1. 1, XOR 4, XOR 1 is 4. If you pop G, you're left with 4 and 1, which is 5. If you pop H, you're left with 2, 3, and 1, which is 0. So if you pop H, you get to a bad state. So H is a winning first move. If you pop V, you get to 2, 2, 1, which is 1. If you pop P, you get to 2, 1, 1, which is 2. And if you pop R, you get to 2, 1, which is 3. Now, one optimization is we could have stopped here at H. We could tell based on the fact that H is a bad state that none of its lower states are going to be bad states. And that just follows from the fact that can't ever go from a bad state to another bad state by the definition of the bad state, right? So if the first player pops H, we're saying that that is a winning move. But then if say P was also a bad state, then that would mean the second player could then pop P, and they will be in the same position as if the first player had popped P, which is a contradiction because we already said H was a bad state. So in general, whenever we get to a 0, we can stop exploring down that chain because we know there's not going to be any more bad states once we have a blue number of 0. But that's just a little optimization. It doesn't hurt to write it out like this. Okay, if you pop I, you get 2, 4, 4, 4, which is 6. Pop F, you get 2, 4, 1, 2, 4. 2s and 4s cancel, leave you with 1. If you pop S, you get 2, 4, 2, 4, that's 0. Great, so S is another bad state. Pop N, you get 2, 4, 1, 1, 4, that's 2. And U gives you 2, 4, 1, 4, it's 3. All right, T gives you 2, 4, 4, 3, that's 1. C gives you 2, 4, 4, 2, that's 0. Okay, and like I said, we can stop here. We know that popping A or L cannot possibly give you a bad state if popping C gives you a bad state. Okay, so the bad states here are H, S, and C, and I'm pretty sure that's right too. Cool, so that's it for number 2. All right. Third puzzle. So I think we've got the workflow down. So let's just keep going through the steps here. We have single bubble F. It contains L, which contains U, contains P by itself, and then it contains H. So H contains R by itself, and E. E contains C and A. C contains V and I. Okay, yeah, that looks like it. 16, 17 bubbles, 16, 17 nodes on the tree. Okay, great. All right, start with the easy ones. 1, 2, 1, 1, 2, 1, 2, 1. Actually, okay, so yeah, we've seen this before. We know that whenever you have this structure that this is going to be a 4, and its orange numbers will just be 0, 1, 2, 3. Same here. Okay, so now we've got 4 more bubbles to fill in. We need some intermediate states here. So V plus I. Then we'll need C plus A, E plus R. And then L, P, and H, which I'll write as L plus P, and then L plus P plus H. Okay. V plus I. 1 XOR 4 is 5. Oh, okay. So here's a trick. Whenever you have one of the numbers 0 through 3 XORed with all of the numbers 0 through 3, the result is going to be the numbers 0 through 3. 1, 2, 3. And that's just because of how XOR works. Okay, yeah. The Nimber addition table here, if you look in the upper left corner, you notice that 0, 1, 2, 3 appear in each row and column exactly once of this first 4x4 grid. So if you XOR 1 into all of these numbers, you're going to get all the numbers back in some order. And that's just going to be true for any power of 2. All the numbers less than that will have this relationship. So you notice that the numbers 0 through 7 is 1 less than 8. If you XOR 5 into all the numbers 0 through 7, you'll get all the numbers 0 through 7 back in some order. And the same with up through 15. All right, just one quick optimization there. So yeah, so I know that 1 XORed into 0, 1, 2, 3 gives me 0, 1, 2, 3 in some order. Doesn't matter. Okay, so that gives, since C wraps this state, its orange numbers are 0, 1, 2, 3, 4, 5. 6, great. Okay, C plus A, 6 XOR 4 is 2. So 4 XOR 0, 1, 2, 3 is going to be 4, 5, 6, 7. 4 XOR 4 is 0. 4 XOR 5 is 1. 6 XOR 0 is 6. I already got that. 6 XOR 1 is 7. Got that. 6 XOR 2 is 4. And 6 XOR 3 is 5. Okay, great. So 0, 1, 2, 4, 5, 6, 7. Three. All right. E plus R. 3 XOR 1 is 2. Probably another trick I can use here, but I'll just go through. 1 XOR 0 is 1. 0, 3, 5, 4, 7, 6, and then 3 XOR 0 is 3, which we already have. H will have 0, 1, 2, 3, 4, 5, 6, 7. I'm just going to write that as 0 through 7. 0, 1, 2, 3, 4, 5, 6, 7. And so H's Nimber will be 8. Actually, we don't need to get, we can stop here. We don't need to get the Nimber of F because we know we're going to need to pop F since it's the outermost bubble. But let's just go ahead and get it just for completeness. All right, so L and P. Yeah, we've seen this before. 3 and 0, 1, 2. And L plus P plus H. 3 XOR 8 is 11. 8 XOR 0, 1, and 2 is 8, 9, 10. I'll put in commas whenever we have multi-digit numbers, just to be clear. And then 3 XOR 0 through 7. Yeah, okay, so this is the shortcut we said earlier. Any number 0 through 7, XORed with all the numbers 0 through 7 is going to be all the numbers 0 through 7 in some order. Okay, so this is 0 through 10 and 11, so 0 through 11 and 12. Okay, so if we just pop F, we're left with L, P, and H. That's 2 XOR 1 XOR 8, which is 11. If we pop L, we've got 1, 1, 8, which is 8. Actually, I can tell that none of these are going to have blue numbers of 0 because, remember, when you XOR it together, you split it into powers of 2. 8 is a power of 2. And so there's not going to be anything on this side to cancel out with that because all these numbers are less than 8. They don't have an 8 to cancel out with this 8. I'll just go ahead and write it out though. Pop U, you've got 1 and 8, which is 9. Pop P, you've got 2 and 8, which is 10. Yeah, so none of those are 0. Okay, if you pop H, you've got 2, 1, 3, 1. 2, 1, 3, 1 is 1. All right, if you pop E, you're left with 2, 1, 6, 4, 1, 2, 1, 6, 4, 1. The ones cancel. 2 and 6 is 4, and 4 is 0. Okay, yep, cool. So E is a bad state. Popping E is a bad state, which means, again, we don't have to explore anything below E because we know that you can't get from a bad state to a bad state. Great, so we don't have to check any of those. And R leaves you with 2, 1, 3. That's also 0. Great, so E and R are the winning first moves. Yeah, E and R are the winning first moves for the third puzzle. All right, cool. Next up, puzzle number 4. A. Yeah, this one we know. It's 4. And we don't need it for this one since it's at the top. So this one we can get 0, 1, 2, 3, 4. So this one is 5. All right, so the only combined states we need are V and S and N and U. 1 and 3 is 2. 0 and 3 is 3. 1 and 1. 1 and 2 is 3. 2 and 3 is 1. 3 and 0 is 3. We got it. 3 and 1 is 2. Got it. Okay, cool. The A, which contains this one, will have 0, 1, 2, 3. and y will have 0, 1, 2, 3. Right, so that's 4, and this gives us I 0, 1, 2, 3, 4. All right, great. So the overall state 4 and 5 and 5 and 2 is, the 5's cancel, 4 and 2 is 6. Pop A, you get 1 and 3, 5 and 5 and 2. 5's cancel, 1, 3, and 2 is 0. All right, so again, we can stop there. We know that none of these states that follow A will be zeros. If you pop I, you get 4, 4, 5, and 2. The 4's cancel, 5 and 2 is 7. So there's actually a slightly more efficient way to get the light blue numbers. I'll go ahead and explain it, but it's a little complicated. So if it doesn't make sense, don't worry about it. You can always just do it the way we've been doing it. So if you have the state with A, I, M, and B, and of course everything inside them, that has a number of 6. So what happens when you pop I? How does the number of the state change? Well, if you were to remove I, completely remove this branch, the resulting number would be 6 XOR 5. Nimber subtraction is the exact same as nimber addition since everything cancels out with itself. So you get left with 6 XOR 5, which is 3. Okay? But if you just pop I, you're still left with everything below it. So imagine you remove this whole branch and you have a number of 3, and then you add back in y and everything below it. So you remove I and you add back in y. So when you remove I, you have a number of 3, and then when you add back in y, you take 3 XOR 4, which is 7. Okay? So in general, any time you want to get a blue number, you can take a number where that bubble's at the top and XOR it with the value, with that bubble's number, and then XOR it again with the numbers of all its contents. So like I said, 6 XOR 5 XOR 4 gives you 7. And so for y, you can take 7 XOR 4 XOR 2 XOR 3. Okay, 7, 4, and 3 cancel, so you're left with 2. So it's a little complicated, but once you remember the formula, it's actually slightly simpler. I'll do a few more just to show that it is a little faster. So for n, it's just 2 XOR 2 XOR 1, which is 1. And then f is just 1 XOR 1, and then XOR 0, you don't have to worry about. So this is 0. All right, so f's a bad state. So u is 2, 3, 2, which is 3. T is 3, 2, 1, which is 0. We can stop there. So m is 6, 5, 4, which we already said was 7. R is 7 XOR 4 XOR 1 XOR 2. And that all cancels because the powers of 2 that make up 7 are 4, 1, and 2. So that's 0. We can stop there. E is 6 XOR 2 XOR 1, which is 5. And then G is 5 XOR 1, which is 4. Okay, so we've got a few here. A, F, T, and R. Awesome, and that's puzzle number 4. All right, number 5. It's all one big bubble. So the process is pretty complete now. The only thing that helps a little bit is to recognize structures you've seen before. Like, we've seen this one a number of times. We know that's a 4, same here. This, I think we've seen before. So something containing bubbles with 4, 0, 1, 2, 3, and 1, 0. Yeah, here we go. So we don't need to redo that. So we know that the one that contains these two will be 6 with 0, 1, 2, 3, 4, 5. And this is the same as the first puzzle. This contains 3 sets of concentric bubbles of size 1, 2, and 3. Yeah, so that's the same as this here, S. So S has a number of 4 with orange numbers of 0, 1, 2, 3. All right, so we just go ahead and fill that in here. All right, cool. So we've only got a couple of combined states to fill in. So we're going to need to get E plus S plus G, and then N plus L. Do E plus S, and then E plus S plus G. And then I'll put N plus L up here. E plus S, didn't we do this one before? 4 with a 6. Yeah, here it is. Okay. Yeah, so we've done this. So we know that when you combine a 6 with 0 through 5 and 4 with 0 through 3, C plus A. Here we go. So the pink number's 2, and then 0, 1, 4, 5, 6, 7 for the orange numbers. 0, 1. All right, great. Now let's add in G. 2x over 2 is 0. And we need to get 2 XORed with each of these. 2, 3, 6, 7, 4, 5. Okay, all right, so since L contains E plus S plus G, L is 0, 2, 3, 4, 5, 6, 7. All right, N plus L, 4 and 1 is 5. Okay, oh, here's that trick. 1 combined with each of the numbers 1 through 3 gives you the numbers 1 through 3 in some order. 4 combined with this will be 4, 6, 7, 0, 1, 2, 3. Okay. F, which contains this, will have 0, 1, 2, 3, 4, 5, 6, 7, 8. So, starts at 8. If you just pop F, you're just left with N and L. 4 and 1 is 5. So pop N, you get 5, X over 4, X over 2, X over 1. 5, 4, and 1 cancel. You're left with 2. 2x or 2x or 1 is 1. And 1x or 1 is 0. 2x or 1 is 3. So for L here, 5x or 1, x or 4, x or 6, x or 2. 5, 1, and 4 cancel, so 6 and 2 is 4. 4x or 4, x or 3, x or 2, x or 1. 4 and 4 cancel, 3, 2, and 1 cancel, that's 0. We can stop exploring that branch. 4, 6, 4, 1 is 7. 7, 4, 2, 1 is 0. Stop there. 7, 1 is 6. 4, 2, 1 is 7. 7, 1 is 6. So P, E, and I. Okay, last two. What was this one again? We've definitely done that. Here, okay, so this S here is a combination of 4, 0, 1, 2, 3, and 1, 0. So that's what we have here. 6 and 0 through 5. We don't need the orange numbers for these. Let's do H plus L first, and then H plus L plus E. And here, yeah, let's just start in the small end and go up. So D plus U plus T, and D plus U plus T plus B. All right. H plus L, 0, 1, and 2 is 3. And here's that trick where I know there's only going to be 3 orange numbers because this only has 3 orange numbers. And I know that 0, 1, and 2 have to be in here because everything after 3 has to be in here. So I know that's what it's going to be. So now, combine this with E. 3 and 6 is 5. So 3 with each of the numbers 0 to 3 is going to be 0, 1, 2, 3 in some order. And so 3 and 4 is 7, and 3 and 5 is 6. And 6 with 0, 1, and 2 is going to be 6, 7, and 4. Okay, so B's orange numbers are 0, 1, 2, 3, 4, 5, 6, 7. All right, so D and U is exactly the same as H and L. D, U, and T, 3 and 3 is 0. And here's another trick. So I know that 3 XORed with 0, 1, and 2 is going to give me 3 numbers. They're going to be different numbers, and they're all going to be less than 4. So 0, 1, 2, or 3. And I know that it can't be 0 because 0 is pink here. So that's 1, 2, and 3. When you do enough of these, you start to notice tiny little patterns like that. Save you a couple seconds here and there. All right, 0 and 8 is 8. 0 XORed the numbers 0 through 7 is obviously 0 through 7. 8 XORed with 1, 2, and 3 is 9, 10, and 11. So A's orange numbers are 0 through 7, 8, 9, 10, 11. Oh yeah, and the overall state is 12 XOR 2 XOR 4. 12 is 8 plus 4, so the 4's cancel. 8 plus 2 is 10. 10 is greater than 8. It has an 8 in it when you split it up by powers of 2. So I know I don't have to worry about anything over here. None of these are going to work out to 0 because there's no way to cancel out the 8. So we can ignore all those. A's blue number will be 10 XOR 12, XOR 2, XOR 3, XOR 1, XOR 8. So the 2, 3, and 1 cancel out. 10, 12, and 8. 8 and 12 leaves 4. 10 and 4 is 14. So now we can do the trick again. 14 has an 8 in its expansion, so there's no way to cancel out an 8 with any of these over here, so we can ignore all of these branches. So 14, 8, 6, 1, and 2. 14, 8, and 6 cancel out. So 1 and 2 is 3. 3, 6, 1, 4 is 0. Yeah, 3 and 6 is 5, and 1 and 4 is 5, so that's 0. So we can stop going that way. 3 and 1 is 2. 3, 2, and 1 is 0, so we can stop there. We didn't have to find many blue numbers at all. All right, great. E and L. All right. Last one. Oh, this is going to be easy. Most of these are equivalent to nim stacks. So the only one we'll have to do is S and Y. Didn't we do this one before? 4 and 4, that sounds familiar. Yeah, here it is, puzzle number 2. So all we need out of this is the nimber for the one above it, which is 1. Okay, great. We don't need to get any orange numbers or combined states at all. Oh, we do need the overall. So 3, 2, 1, cancel. 6 and 5 is 3. Okay. 3 XOR 3. XOR 2 is 2. 2, 2, 1 is 1. 1 and 1 is 0. 3, 2, 1 is 0. We can stop there. 3, 1, 4, 4. The 4's cancel, so 3 and 1 is 2. 2, 4, and 3. 2 and 3 is 1. 1 and 4 is 5. So we can stop here because when you break down 5 into powers of 2, it has a 4 in it, and nothing below it is 4 or greater. So we know that that will never cancel out to 0. 2, 4, 2, 1 is 5. Okay, so same thing here. We can just stop. 3, 6, 5 is 0. All right, we can stop there. 3, 5, 4 is 2. 2, 4, 3 is 5. All right, and we can stop here because none of these is 4 or greater. Okay. So W, N, R. All right, and that is how you solve Bubbly by hand. I have been checking the results we get against the program just to make sure that we were doing it right. And then the last step is the same as if you had done it with a program. You just circle all of the letters in each of them that are winning first moves and extract them across like this. All right, the end. That's it. If you actually watched the whole thing, thank you very much. It turned out much longer than I expected. I hope it's clear at this point that I really enjoyed this puzzle. I'll wrap up by talking for a couple of minutes about my idea behind this video. My original plan was a little bit different. I had solved this puzzle in 2019 during the mystery hunt, basically by writing the good state, bad state program from the first half of this video. I did not know the Sprague-Grundy Theorem at the time, but I recognized it as an impartial game, and I had heard people say, oh, the Sprague-Grundy Theorem can solve any impartial game. So I decided that I would come back to the puzzle after Mystery Hunt, learn the Sprague-Grundy Theorem, and solve the puzzle the right way. Programming is very useful in Mystery Hunt, but there are usually only a few puzzles that actually require it. So I suspected pretty strongly that if you had the right tools, you could solve this one without programming. And so that's what I did in the first version of this video. I tried to learn the theorem and apply it while recording the video without knowing ahead of time whether it would work out or not. And I got stuck. There's hours of footage of me getting nowhere because I couldn't figure out the trick with the orange numbers. Finally, I sort of gave up and looked at the given solution for the first time, and the given solution does not have a way to solve it without programming. So suddenly I didn't realize whether it was going to be possible at all. But I kept at it, and eventually I did figure out the trick, and I was able to end that first version of the video basically the same way this one ends, working it out by hand. But in the end, that version would not have made a good video. It was 12 hours of footage, and half of it was me saying things that I later had to correct, or things that were incorrect but I never actually came back and corrected them. I wanted people watching to be able to learn the topic as well, and that version would have just been confusing and probably longer than 3 hours. So I was not able to use that footage, but now that I knew the answer, I liked it even more than I had expected to. I originally thought that the Sprague-Grundy Theorem would just be a formula that you could plug the problem into and get the solution out, but it turned out to be much more complicated than that, more challenging. So I still wanted to make the video, so I went back and re-recorded everything, and that's this version that is hopefully more coherent. So this video is a bit different from a typical solve-along video, and I'm leaning toward not making other videos like this one in the future. I really like the idea of teaching tools that are useful in puzzle solving, but I'm not sure that a video is the best way to do that. If I do make another video like this one, I definitely will not try to teach the tool at the same time as I'm learning it. Also, I'd probably focus on tools that come up more often in puzzle hunt style puzzles. I mean, the Sprague-Grundy Theorem is a great, very well-known topic in recreational mathematics, but I looked and I was not able to find any other mystery hunt puzzles where you could actually apply the Sprague-Grundy Theorem to an impartial game other than Nim, like you can in this case. But who knows, maybe we'll see more in the future. So that's it for this video. Thanks again for watching, and I'll see you next time.